Hello, everybody. Good morning. Hope everybody is enjoying PyCon. It's a pleasure to introduce you Damien, and it's an honor too. We all know him as the creator of MicroPython and the ecosystem around it. So he has a background in theoretical physics, robotics, and computer engineering, and he loves to program. And we all love to do that, okay? So welcome to PyCon, and I hand it over to you now.
Okay. Okay, thanks, Sonali. And hello, everyone. Welcome to the IoT mini conference, and thanks for coming to my talk. I gave a couple of talks last year, and maybe you heard them, maybe you didn't. But this talk is sort of independent, but also a little bit of a follow-on of the things that have happened since in the last 12 months with MicroPython. And I hope to just tell you a bit about MicroPython for those who don't know about it, give some demos, and tell you what some really cool applications that it's being used for in the real world or out in the wild, as this picture is depicting. Okay, so MicroPython is given by this little logo in the middle there. All right, so this is kind of like my spiel slide, my elevator pitch slide. But there's a big opportunity these days in electronics and microcontrollers because there's lots of really cool components that you can buy and use, like software-defined radio things we heard about in the previous talk. Cameras, gyroscopes, accelerometers, motors, really great sensors and actuators that you can use to build really cool devices, Internet of Things devices. But the problem with these things is they're really complicated to use. You have to read through lots of data sheets and understand registers and understand lots of things to use them. So there's an opportunity. Now, we know that from a desktop programming, so everyone uses Python because it's so much better than C. But from I mean, it's true though because Python is a high-level language and you can get things done more quickly and it's cheaper from a cost of programmer point of view because the programmer is more efficient. And you write a web server in Python very easily. You don't write a web server in C because it's really hard and parsing JSON in C is really not fun. You can do it, but it's easier to do it in Python. And similarly, on a microcontroller, which is traditionally programmed in C, the idea is to use a high-level language like Python so that you can more easily get your devices running much more quickly. So it takes you a day instead of a month to build some cool device. So it lets beginners come on board and do things they couldn't do before because they've now got access to microcontrollers via Python. And also people who are very familiar with the field can get things done much more productively. So that's sort of the spiel for MicroPython. But what exactly is it? So it's a complete re-implementation of the Python language. So it doesn't take anything from the C Python implementation. It's all written from scratch. And it was designed from the ground up to be very, very efficient with resources and not use much memory and not use much code space, which is important, and to also be efficient when executing. So, normal Python running on your desk takes megabytes of data of RAM to run in, if not hundreds of megabytes. But MicroPython can run in about 8 kilobytes of RAM, so 1,000 times less. It's also designed to run without an operating system, so directly on top of a bare metal, as I like to say. So you have the microcontroller or a Raspberry Pi or anything, and there's no operating system, it's just MicroPython running straight on top of that. So you can think of MicroPython as the actual operating system itself, and the Python prompt is the only way you can interact with the computer. And it gives you a real feeling like you have a master control of this machine. So MicroPython includes the familiar REPL that you're used to, the read, evaluate, print loop in Python, so you can do stuff interactively. And it has some of the Python libraries like the JSON module, but in MicroPython everything starts with a U for micro, so it's called UJSON, and so on. And there's also extra modules in there to control hardware, and I'll show a bit of those later on. So if you want to try out MicroPython, it runs on lots of different boards. There's the Pi board, sorry for the really low quality resolution pictures, but there's the Pi board there, and then there's a microbit, and then there's the ESP8266, and then there's the ESP32, and then there's the text instrument CC3200. Then there's the Adafruit circuit playground. There's lots of boards it runs on. You can even run it on your PC. You can even run it in the browser, and I'll explain about that a bit later. There's some links here you can go if you want to buy or download or try it out. So I'll just quickly do a demo for those who haven't seen it, and for those who have seen MicroPython before, hopefully the demo is something slightly new for you. Okay, so I have, you don't really have to see much, but this is a board in a nice little purple housing, and it's connected to a sensor, an accelerometer sensor, and a servo motor on the output. And then to the computer via USB, just so I can type commands. And here, so is the prompt. So this is running directly on the board, and I can do simple things like addition and stuff. Okay, but I want to do something a bit more interesting than just addition. So the machine module has some really useful things for working with microcontrollers. For example, an I2C class. So this is a way to communicate with sensors. So I create an I2C object, and then I can scan the bus for devices. So it's found 4 devices, and one of them, the number 107, is the gyroscope that I want to work with. So I can read from the gyroscope, address 107, and I want to read the gyroscope's memory, say at address, what are we doing? Address 20. And I want to read 1 byte, okay? And it's normal Python, so I can use like bin convert to binary underscore is the previous expression. Whoops, okay, bin of, all right, so it's hex f because it was a byte string, it was not an integer. Okay, so this is the value of the register OX20, and if I go to my data sheet just quickly, so this is a list of all the registers in the gyroscope. And control register 1 is at address OX20, and it tells you all the bits there. Now, I actually just need to, because I did this demo before. Okay. So read from that value. Now, it's actually got, okay, I'll do it properly this time. Okay, when I reset the gyroscope, that register has values just 111 at the end. So that means that the X, the Y, and the Z axis of the gyroscope are enabled, but it's actually in power down mode. So if I start to read data from it, read from mem at 107. Don't worry about the X80, that's just so it increments the memory address. And I want to read 6 bytes from address 28. If I go back to my data sheet, address 28 is the output X low, and that's followed by output XH, YL, YH, ZL, ZH. So they're the data registers of the gyroscope, the X, Y, and the Z axes. So if I read 6 bytes, I get this is the raw data from the gyroscope. And if I move the gyroscope around, nothing's happening. The data is all the same. Okay, so I've actually got to enable it. So write to the register. So this is enabling the okay, it needs to be a buffer, a bytes object. Okay, so now I've enabled the gyroscope by writing to that control register. And if I read the data, it now changes as I move the thing around. Okay, but this data is just bytes. Now I have to interpret it. So it's actually in 16-bit signed format. So I can use the struct module. So in Python, things are really easy. So import struct. So let's get some data and save it in a variable. So I want to interpret that. So struct.unpack and little endian signed half word 3 values for X, Y, and Z. Okay, so that's my gyroscope X, Y, and Z value. Okay, so now that we know how to get the values from the gyroscope, let's make a loop and extract, import time first. So forever data, to extract the data, values, just use the very quick So extract the data there and then print vowels and let's sleep for, say, 50 milliseconds. Okay, so this is the raw gyroscope data, and if I move the gyroscope around, so if it's stable, it's close to 0, but if I move it quickly, I get really big numbers, depending on if I'm rotating left, right, or whatever. Okay, so that's a really quick way to start using an I2C sensor, and it's like super quick, and you can use all your Python abilities, struct module. Let's just do one more thing, create a servo, and we'll control the servo from the gyroscope, if I could get it. Okay, the history's still there. So extract the data, get the values, print the values just to show you what's going on, and servo, set the angle of the servo to say the z-axis divided by 100 because the numbers are very big, and then sleep for 50 milliseconds again. Okay, so now if I, all right, no, it's going a bit crazy, really. All right, so it should be, if I rotate this, so in the z-axis, it's going, okay. So it's actually the derivative of the angle, because the gyroscope is telling the change in angle. If I don't change anything, the servo stays still. But if I move left, it moves to the right. Well, if I move that way. It's only when I move does the servo actually move. Okay, that's how gyroscopes work. They're the derivative of the angle. Okay, so that's the end of the demo, but it shows you how quick and easy it is to get something working. So yeah, you might still need to read a data sheet to understand things, but it's easy to implement that data sheet. And also, hopefully, and in this case for this sensor, it's there, someone's written actually a Python module that you know, allows you to provide a class and some methods like get gyroscope X, Y, enable gyroscope, disable gyroscope. And it's quite a simple wrapper, and then you don't even have to read the data sheet. All right, so, okay. That's the live demo. So what's happened in the past year, so it's a 12-month recap of advances in the software of MicroPython. I think the biggest thing, which I should have done at the very, very beginning, was implement help modules. So help modules, if you type it, it tells you what modules are available in your current implementation of MicroPython. So help, I hope this worked, help modules, okay, there you go. So this is a list of the modules that you can use on this board. So this is the important thing is sort of discoverability. So I've got a Python board, and how, you know, what can I do with it? Well, you know, I can import random, and then press tab, and it will tell me what's in the random thing. So I can do, you know, rand int. We all know how that works, from 100 to 400, and then yeah, so on. Okay, so help modules. Yeah, is a really useful thing, and by the way, that's exactly how you do it in normal Python. So it's the same thing. Your knowledge goes from MicroPython to normal Python. MicroPip. So pip is used to install modules on your computer for normal Python, and you can use it in MicroPython to install things. But because you don't have a bash prompt or something, you actually have a module called upip. So you do import upip and upip.install, and then you can install modules on the PyBoard. It's got to be connected to the internet, though, obviously, for that to work. But yeah, that's actually implemented and working. There's some modules for the Internet of Things, like async.io, so you can create a HTTP server that can have multiple connections. So that mirrors how it's done in normal Python with async.io. There's a module umqtt for doing simple messaging in the Internet of Things. There's things that have been added to help reduce memory usage. So ujson.load, so you know load s will parse a string, but load, you can pass it a file and it will read it, you know, as it goes, instead of loading the whole string into memory. Same with uzlib.decomp.io, so instead of having to hold the whole file in memory and decompress it all at once, you can decompress it as a stream. So this helps ports that don't have much memory and they just want to read things in one at a time. There's also a virtual file subsystem that's been added, so you can mount multiple file systems, an arbitrary number of them, under MicroPython. You can even implement a file system in Python. So you write a class, and that class has to have lister, get CWD, open, and all the things that you'd expect the OS module to have to do file system things. If you write a class that implements those basic functions, you can actually mount an instance of that class under the virtual file system and then use normal lister and open and stuff on that class. So it's pretty powerful in that sense. So you can have a normal, like a fat file system living alongside your own Python file system and other things. On the ESP8266, they've implemented inline assembler. There's been addition of soft IRQ handlers so that you can now allocate memory during an IRQ, although it's not as, the latency is longer. These are all quite technical things. Threading has been implemented on PyBoard, so you can use the _thread module and have multiple threads of code executing at the same time. And it's also, MicroPython's been ported to the Zephyr operating system, which is the Linux Foundation's sort of IoT operating system. So MicroPython can run on top of that, which means it can run on lots of different boards. This list is pretty long. There's lots of stuff's happened in the year. Support for double precision floating point. And then there's been lots of bug fixes, minor things like 0 to the power of -1 will now raise an exception, for example, where before it just gave you NaN. So lots of edge cases have been fixed from people finding small bugs. Refining compatibility with CPython, so you can now hash floats, for example. I don't know why you really want to hash a float, but well, sometimes you want. Because if you put 1.001 in a dictionary and 1.0011, it's like it's a bit strange because the same float maybe will hash different things if it's slightly different. Anyway, some people like to hash floats. The code size has been actually reduced whilst features have been added. There's less stack being used, and test coverage is up from 94% to 98%, and the last 2% is really tough to get, so how further that will go. But do note that the first version of the PyBoard from the first Kickstarter that was done over 3.5 years ago is still supported, and all these new features are all available for it. So if you have one from a long time ago, you can just install the latest firmware and you get everything. You get threading and all these cool things. Okay. So another cool thing that we've developed, you can run MicroPython in the browser by using this thing called Unicorn, which is an M-scripted version of a QEMU CPU emulator. Lots of technical terms in there, but basically it means you can go to this web address and you'll get a prompt, and it's really MicroPython in the browser on a simulated ARM core. So you can actually do inline assembler in the browser as well. Like you're really running on an ARM core there. And there's a little picture of a PyBoard there. You can connect a servo motor to it. You can click the buttons. You can make the LEDs turn on and off in exactly the same way that you would use the real hardware. So, I mean, yeah, I won't show it to you because there's not enough time to do a demo of it, but just go to this address and try things out. It's still in beta. There's a few bugs you may find, so just refresh your page if things crash. But you can select things like your RAM size, and it has a little clock speed indicator. I think it gets up to like 1 megahertz or something in the browser. But that's been a lot of fun developing. We have a new LCD screen that you can get, which and you can duplicate the REPL on it, so that this is like outputting the actual Python REPL on the LCD. And we also have these really fancy housings, which are made of machined, anodized, and engraved aluminium. And you can have a look at one up here at the front later on if you're interested. Okay, so that's sort of the advances. I just want to go on and talk about things, so where MicroPython's being used in the wild or out there in the real world. And we have some people who are using MicroPython, embedded engineers whose job it is to make devices for people on contract. And they're using MicroPython because it's a really great way to build products really quickly. You start with you have like a PyBoard and you get MicroPython running on it. You develop your application, you prototype it very quickly, and then you refine it. You maybe make some custom hardware because you really need it to be better or smaller or faster, and you might write some code in C to replace the Python bits that you need to run faster. But eventually you end up with a product that's using MicroPython sort of as the application level layer, or as the logic, the glue logic of your system. And it's been used in a traffic measurement device, which has actually been certified by a National Institute of Measurements. So that's actually in use. MicroPython's being used in a real world device. It's used in a way to measure some things optically for medical use, and it's currently being designed into a device that will help brain surgery. So it's not just a toy; it's actually useful in real industry. It's also used in education on the BBC Microbit, and there was recently a program where microbits were taken to Africa to help students at school teach them about computers and things with really hands-on experience. So there's a tiny little microbit with a smiley face of red lights in the bottom left there, running MicroPython. So that's really cool. It's reaching lots and lots of people. And it's also being used by hobbyists who are sort of our core user group, I guess, who make all sorts of weird and wonderful things out of it. So on the left here is a barometer, so a weather station, and there's 3 sensor nodes placed sort of around the house, and they're all running MicroPython and transmitting over some some radio. It's not Bluetooth, but it's 2.4 gigahertz. Transmitting their battery status and pressure, and this thing will then log it on an SD card and output it on an e-paper display. And there's a quadruped robot up there with lots of servos, which is being controlled by MicroPython. And then on the bottom right, there's a 2-wheel balancing robot that has a gyroscope, like I showed you before. And it has a couple of motors, and it has a radio control, so you can remote control it. And MicroPython will sit there, will read the gyroscope and the accelerometer to work out its current angle, and then adjust the motors accordingly so that it's balanced. And also, if you use the remote control, you can move it around. So people can build really cool things with MicroPython. And I guess these are Internet-y of things because they use microcontrollers, and they use wireless communication. And I said this last year, but that, to me, Internet of Things is really this combination of microcontrollers and embedded devices that are communicating over the wire, over the air. So it doesn't have to be like a coffee machine that's connected to the internet and tweets. It can be something like a robot that's controlled over the air. I mean, it's still it's communication, and it's microcontrollers, and it's technology. The other thing here on the left is this called a Pi guitar. So with guitars, you have all these knobs and levers to adjust all the different properties of the electric guitar, how it works. And this guy wanted to sort of soup that up, so be able to control even more things on the electric guitar. So he used the Pi board in that and wrote his code in MicroPython, and added all these extra electronics to sense the guitar and control it. And I'm not a musician, and I don't really know about how it works, but he had this massive array of electronics, and he was like, MicroPython, you really helped me do this because the programming was so easy, and I could make this really cool thing. And he has all these videos of his Pi guitar. It's pretty cool. And then on the right here is a quadcopter. So this is actually something I started a long time ago, wanted to get working, and I've only just got this thing out of the cupboard and dusted it off. And one aim is to show that MicroPython can actually control a quadcopter in real time. And this is the ultimate example of having something. You don't want it to crash. You don't want it to run out of memory or pause because it's doing a garbage collection. You want it to actually, right? Like you got your quadcopter hovering there, and it cannot pause for a moment to think. It's got to keep those motors spinning so that it doesn't drop out of the sky. I know it can be done. It just has to be. Well, the proof is in the actual code, right? So the idea is to make some code and publish a nice demo of how you can use it to build a quadcopter, and then control it also with remote control over the air. And then maybe go further and add like localization things and make it really cool. So these are the sorts of things MicroPython is being used for. And there's lots more. This is just a sample that I wanted to give you. And you can go online and search for MicroPython. And there's YouTube videos, and on the forum there's lots of cool stuff. There's also been a book written recently by a good friend, Nicholas Tullavy, who was a real champion of the microbit. And this is an O'Reilly book about MicroPython, so this is really cool. It's like a milestone. It's aimed sort of at the beginner and gives you an overview of different boards and what you can do with them and how to use MicroPython. And I think it's only early release at the moment online. I don't think you can buy a hard copy just yet. I wrote a foreword to it, so yeah, you can read some of my words if you get that book. But yeah, so that's the end of my talk. But so micropython.org is where you can go to read information. The forum is where people discuss things. On GitHub is where all the code is developed. And there's this new unicorn thing which you can try out if you want. It's linked from the main website. But yeah, that's all I had to say. And I guess I have a few more minutes left for questions. So. Thanks.
Any questions for Damien? Yeah.
Hi. So I'm currently doing embedded programming in C, so I'm very much interested in switching to Python. I noticed there's some commercial support, like this PyConAU, a European company, and Adafruit with some of their feather boards.
Yeah.
They have MicroPython or CircuitPython implementations.
Yep.
As the creator of MicroPython, what's your view of these commercial efforts?
Okay, so yeah, good question. So think of MicroPython as sort of a Linux kernel, and that people are making distributions of it, like there's Ubuntu and Red Hat and Arch Linux and so on. And so there's MicroPython, and then there's sort of my distribution, which is like official MicroPython and the PyBoard. And then there's Adafruit with their CircuitPython, so they've taken MicroPython and rebranded it as CircuitPython. And underneath it's just MicroPython, but they've got a few extra, their philosophy was that they wanted to make it easier for people to use, easier for beginners to use. And they think that normal MicroPython is not easier. I would disagree. But they just had a different mentality. I mean, it's like the difference between Ubuntu and Red Hat and Arch Linux. It's just different for different sort of people. And they've created different libraries for doing I/O. It's just a different way of doing I/O and I2C. And PyCon as well have taken it and created their own line of boards. And they're a very commercially oriented company, PyCon. Very confusing. It sounds I always mix the two, but PyCon, they're creating boards with LoRa and Sigfox connectivity. So that's their main slant, and they're using the ESP32 as their core chip. So these are technically competitors to me in that I'm trying to run a business. George Robotics is the name of the business, selling PyBoards and stuff, but I'm also developing the core software which all my competitors run. So basically I write software for my company and all my competitors' companies. But you know, you keep your friends closer and your enemies even closer. So if you write your enemy's software, then I guess you got them in the palm of your hand. But that's the state of play. And my philosophy is, look, let MicroPython flourish, and if it's going to be other people taking it and doing that at all.
Thanks for a great talk, Damien. I was wondering if you could share with us what's upcoming in MicroPython.
Okay, so what's in the next talk? Yeah, so, well, I'm doing work at the moment, still doing work for the European Space Agency. I've been doing it for quite a while now because they want to use MicroPython to control satellites. And there's been some really good progress there to make MicroPython actually ready to go on a satellite. There's no, you know, these things have timescales of 5 years, so, and there are plans for MicroPython to perhaps go into space, but it's early days and things can always change. So look at that in the next couple of years. But in terms of, I've also been developing version 2 of the PyBoard recently. It's taken a lot longer than expected, but hopefully it will be really cool when it's released. There's just currently a very, very long lead time on microcontrollers of the order of 6 months. So that's really set us back. But look out for a new version of the board with lots of cool features. And in terms of software, I'm concentrating, well, I think there's been a lot of advancement in software in the past 6 months, and more concentrating on applications and things that MicroPython can be used for, and making demos and tutorials and things to help people get on board. Okay, but thanks for the question. It was a good question.
Any more? Oh.
Hi, I'm wondering, is there any sort of scope or possibility to make like a Power over Ethernet enabled PyBoard?
Yes, you can. There's definitely scope. The ST line of chips that have Ethernet built into their hardware, that MicroPython runs on those already, so that's a good start. MicroPython doesn't have built-in an Ethernet support. It can do Wi-Fi, just because that's more interesting, but adding Ethernet is sort of not too hard. You know, all the building blocks are there, you just have to put them together. And then the Power over Ethernet bit, that's more of a hardware thing than a software thing. So you just need to build a board that has Power over Ethernet capabilities and then put MicroPython on it. That's not on my horizon, though, but there's no reason why someone else can't do it.
Thank you.
Thank you, Damien. That was a lovely talk. And I must...
I get a cool mug. Thank you very much.
There's a cup of coffee in there.